In this video we will treat some illustrative examples of the Fourier series expansion. In these examples we will use the Fourier analysis and synthesis equations, in which the signal xp of t represents the periodic signal with fundamental period t0, which equals 1 divided by the fundamental frequency f0. The weights alpha k represent the spectral content of the periodic signal xp of t. The integral of the analysis equation is taken over one fundamental period t0. Where we take this integral is not important, as long as it involves only one fundamental period. For example, we can evaluate the integral from 0 to t0, or from minus t0 over 4 until 3t0 over 4. Finally, this phasor integral property plays a crucial role in the development of the Fourier series expansion. The integral of a phasor with frequency k times f0 is always equal to 0 except for k is 0. A generalization of this property is given in this equation. Thus the integral of the product of two phasors with harmonically related frequencies k times f0 and L times f0 respectively is always equal to 0 except for the case when the frequencies of both phasors is the same. In this first example we will show how this basic phasor integral property can be used to find the frequency content of a very simple periodic signal which consists of only one sinusoidal signal with a known frequency 2 times f0. The exact value of the fundamental frequency f0 is not important in this example. Because of the fact that the signal is periodic, we can write it as a sum of weighted phasor components from which the frequencies are harmonically related. Then, using the Fourier analysis equation and Euler to split the periodic signal xpt into two phasor components, this results into two integrals which clearly represent the general phasor integral property. The first integral is 0 for all values of the index k except for k is 2, while the second integral is only non-zero for k is minus 2. This leads to the result that the spectral content of the periodic signal xp of t is cosine 2 pi times 2 f0t is 0 for all frequencies except for the frequencies plus or minus 2 f0, where the spectral content is given by the values alpha 2 and alpha minus 2 is 1/2. In the second example, we will evaluate the spectral content of a signal which consists of a sum of 3 sinusoidals. But first we will verify if the signal is periodic. We can calculate the fundamental frequency by applying the greatest common divisor operator to the available frequencies. Thus the signal xt is a periodic signal with a fundamental frequency of 50 Hz in this case. By using Euler for each of the sinusoidal components and writing the frequencies of the phasor components as an integer product with the fundamental frequency of 50 Hz, we obtain the values of the spectral content of the periodic signal as depicted in the figure. Note the symmetry in this plot, which is a result of the fact that xt is a real signal. It's not always necessary to find the weights alpha k by using the Fourier analysis equation. We will show this by evaluating the spectral content of a squared sinusoidal signal. The original sinusoidal signal, in red, has a frequency of 2 Hz. Thus, its period is 1/2 is half a second. We can find the fundamental frequency of the squared signal, in blue, by using Euler, which can be written as a dc plus a sinusoidal term from which the frequency is twice the frequency of the original sinusoidal. This implies that the squared sinusoidal has a frequency of 4 Hz and the weights alpha k are given in the equation and represented in the spectral plot. Note finally that the fundamental period is t0 is 1 over f0, which equals a quarter of a second. In this example, we will evaluate the weights alpha k of an ideal periodic square wave as defined in the mathematical equation and depicted in the figure. Usually, we first evaluate the DC component alpha 0 separately. This integral represents the surface under one period of the periodic signal normalized by t0. In this case, this results in the value alpha 0 is 1/2. For k not equal to 0, we can use the mathematical equation of the ideal square wave, which results in the integral from which the boundaries now are between 0 and t0 over 2, because the ideal square wave is 0 outside this region. Before we can use the fact that the integral of an exponent is equal to the same exponent, we first have to change the integral variable t into the same variable of the exponent. This implies that we have to multiply the integral variable t by the constant minus j 2 pi divided by t0 multiplied by k. When multiplying with a constant, we also have to divide by the same constant. By doing so, we obtain the exponent divided by the constant minus j 2 pi divided by t0 over k, and normalized by t0, which has to be evaluated in between the boundaries 0 and t0 over 2. Writing out all parameters, this results in the given expression, which can be simplified by using the fact that exponent to the power minus j pi over k equals minus 1 to the power of k, resulting in this final expression. Combining all results gives alpha 0, which is the DC value of the ideal square wave, equals 1/2. For odd values of the index k, the complex spectral weights alpha k are equal to 1 divided by j pi k, and for all even values of the index k, the complex spectral weights alpha k are equal to 0. The values are represented in the following spectral plot of the given ideal square wave. From the Fourier synthesis, we know that any periodic signal can be written as a possible infinite sum of weighted harmonic-related phasors. The weights are given by the complex value alpha k as depicted in the spectral plot. In other words, we can synthesize or compose the ideal square wave with the following mathematical equation. Then, by combining the phasor components with the same but opposite frequency together and using Euler, we can write the ideal square wave as an infinite sum of weighted harmonically related sinusoidals. In practice, we always will break down the infinite summation, say at capital letter N of n terms. If we use the first non-zero terms up to k is plus or minus 3, the approximation is as depicted in the figure. By using more and even more terms, the approximation becomes better and better. However, at the location of the jump discontinuity of the ideal square wave, it can mathematically be shown that the overshoot cannot be reduced to less than 9%. This is the so-called Gibbs phenomenon. In some cases, the spectral content of periodic signals can be related to each other. For example, assume signal yp of t is related to the periodic signal xp of t by shifting it in time over t0 seconds by scaling it in amplitude by a factor of A and applying an offset of C. Then the signal yp of t will have the same fundamental period t0 is 1 over f0 as the periodic signal xp of t. Thus we can write the periodic signal yp of t as a sum of weighted, harmonically related phasors in which the weights now are denoted by beta k. Using the mathematical description which describes the relation between yp of t and xp of t, and then writing out both summations, we can compare the weights of each of the individual phasor components. This results into the following relations. Only the DC component beta 0 is adjusted by the offset c. Furthermore, all weights beta k are scaled by the factor a. And finally, the time shift t0 results in a multiplication with complex exponent e to the power minus j 2 pi f0 t0. As an example, the square wave xp of t, as discussed before, is used to create a new square wave yp of t, which is related to xp of t as denoted in the equation and depicted in this figure. We have calculated spectral weights alpha k before. Now we can apply the time shift, scale and offset parameters, which results into the equations for the spectral weights beta k of the periodic signal yp of t. Using all these parameters results in the given equations. We've seen before how we can construct an approximation of the periodic signal xp of t by using more and more spectral weights alpha k. Of course, we can do the same with the new periodic signal yp of t. By using more and more weights, the approximation becomes better and better. From the resulting figure we can see that indeed the result is a time-shifted, scaled version of the original periodic signal with an offset. Many waveforms can be synthesized with a weighted sum of harmonically related phasors. The assumptions made up to now are that amplitude, phase and frequency do not vary in time. However, in practice this is not true for many real-world signals. In order to represent the spectral content of such a signal on a plot, we need time as an extra dimension. In these figures we see two examples of such spectral plots. The horizontal axis denotes time, the vertical axis denotes frequency, and the magnitude of the spectral weights is denoted by a color. The left-hand plot is a spectral plot of the word bat, which sounds as follows.
Bat.
In the middle part of this plot, we can clearly see the harmonically related frequencies of the sound ah. Such spectral information can typically be used in practice, for example in voice recognition systems. The right-hand plot is the spectral plot of a whistle, which sounds as follows. Also here, the harmonically related spectral components are clearly visible from the plot. This ends this video in which we discuss some examples of the Fourier series. Thank you for your attention.